Okay.
Okay, so welcome everybody. Sorry for the delay. Today we have Thierry Combot speak about symbolic integration on planar differential foliations. Okay.
So thank you for inviting me, and I will present you an integration problem, indefinite integration problem. So first, consider a differential equation, non-autonomous in one dimension. So y prime, the derivative of y is a function of x. It's a function, a rational expression of x and y of x. This is some differential equation, and what we call the first integral of this is a function of x and y, such that which is not constant, and such that it is constant along the trajectories. So it means that when I differentiate in x this function f taken on x and the solution y of x, so this is equal to this partial representation. So dxf plus this straight f, which is the rational function for defining the equation, times dyf equals 0. So it means that this function f, its levels describe, in fact, the solution of this differential equation. So, of course, sometimes you have a very simple solution like algebraic curves, and then you can find the first integral, which is rational. But typically, these first integrals, either they are only locally defined, and so, in fact, this does not give you nice algebraic information. But sometimes they are also more complicated and rational, like first integral using logs and so on. And we have quite more general definition, but not the general classes of first integral than rational. So we'll consider 4 types of symbolic first integral, and somehow there is understanding that they are the most general ones. So there is, of course, the case of the rational first integral. So you have a rational function in x and y, which is constant along the curves, the solution curves. So it means that, in fact, your differential system has only algebraic solutions. Then there is a slightly larger class, which is the Kader-Boxian first integrals. It means that the y derivative of f to some power is a rational expression. So what does it mean? It means that this y derivative of f is some algebraic function. But if you recall, this partial differential equation here for f requires also that this dx of f will also be algebraic. So in fact, this Kader-Boxian case, it means that our function, first integral function f, is the integral of some algebraic one form. Then we have more complicated situation, Liouvillean first integral, where so this second derivative in y of f divided by the derivative of y of f is rational. So in this case, this means that when you integrate in y both ways, so you can also obtain the same expression, but for x, also using this partial differential equation here, you will obtain an expression for the derivative in y of f and the derivative of x in x of f, which will be, in fact, an hyper-exponential function. It means that it will be something which can be written as exponential integral of some one form, rational one form. So again, this is some generalization of this Kader-Boxian case, because the derivative of y of f is no more algebraic, but it's some exponential integral. And at last, these riccati first integrals. So they are more difficult to define. So these are functions which are quotients of two solutions, two solutions which form a basis, two functions, sorry, which form a basis of solution of some differential equation of second order, like this. So the derivative, second derivative in y of f divided by f equals some rational expression in R, in x and y. And in fact, for each class, this is more and more complicated. there is they correspond to some Galoisian action on the foliation of the solution of this differential system. The rational first integral, essentially all solution algebraic, there is nothing. The Kader-Boksian first integral, it means that somehow we can you have two transformations on this foliation. You can add a number and or multiply the number. The level. If there is some action on the level of this first integral f. So if I take the level f equal h, the action, this Galois action, it will shift h by adding a constant, or in the Kader-Boksian case, multiply this level by some root of unity. For Liouvillean first integral, this is an affine transformation, and for Riccati first integral, this will be homographic transformation. And in fact, we can prove that if you want first integral which are differentially algebraic, then you should be in one of these four cases. So why I introduce this? I introduce it because I am interested in the integration, so undefined integration of such kind of integral. So I take a rational expression in x and y of x, and I wonder in which case I can obtain a nice formula, let's say, for this. So if the function y is algebraic, then in fact this integration problem is integration of an algebraic function, and this is quite well known. So even if it is difficult, this is well known, and the techniques are completely different. So we will not speak about integration of algebraic function, but only about transcendental. In fact, if you take y, a transcendental solution of a differential system on the plane, and naturally you can change the initial condition, and there is a Galois action which will send, in fact, any solution, so almost any, to almost any other. And because of this, instead of doing this integral, which has no parameter, we can replace y of x by y of xh, which will be a general solution of this differential equation. H is a parameter which, in fact, encodes the initial condition, and then replace y of x by y of xh, and now define some integral which will depend on some parameter h. And now, when you see like this, you see, okay, it looks like a lot these problems of integration with parameters. And typically, when you have an integral like this, where y is algebraic, you say, okay, I can have some understanding of I by using creative telescoping. So creative telescoping, it means finding some operator, differential operator in H, such that when I apply this to this integrand, then the integral becomes exact. So the good point when y is algebraic is that it is always possible. But we will see that, in fact, when y is transcendental, it is sometimes possible. And when it is possible, it means that this function, this integral I, has quite some nice properties. Okay. So here is the first result. So if this integral, parameterized integral I of xh, satisfy a non-constant differential equation, so which will be polynomial in x, y, and all these derivatives in h of y, and also all these derivatives in h of the integral I, then up to some parameter of change in h. So you can always replace h by some analytic function of h, because it encodes, in fact, the initial condition. Then this first integral I will satisfy a differential equation of the following form. So you will have some operator L. This L will be a differential operator in h. This will be equal to so this function, so the derivative in h of I of y to some power, integer power, which will be the order of L, and times h, where h is some rational function. And in fact, we have more precise description of possible operator L. So when you have a Kader-Boksian first integral, then your operator, in fact, it will be with constant coefficient. So this is something which is very strange, because when you have when you make a creative telescoping on an algebraic integral with parameter, typically your telescoper, so this operator in H, has non-constant coefficient. But here, in fact, when it is transcendental like this, automatically you have only operators with constant coefficients. And even more, you have some, you see a regularity. So all powers of DH are not possible. So only some multiple of K. So when you are in the Liouvillean case, so it means Liouvillean, but not Darboux-Yan, then in fact, the only possibility for L is some power of DH. And when you are in the Riccati or differentially transcendental, it means no first integrals. Then the only possible operators are 1 and DH. So this L will be called the telescoper, and the other part, so DHY to some power times H, this will be the certificate. Okay. So now I will explain you what we can do when we have this kind of telescoper. So if you find some operator L like this, then it will imply that your integral I, so this integral is a function of x and the parameter h. So of course, this integral satisfies the second equation, dx of I equal g, because it was our integration problem. I is the integral of g. And we have another equation in h, so in the parameter. And the nice situation is that now this system, as a two-variable system in x and h, it will have a finite dimensional space of solution. So you see, this is a linear system, linear PDF system, and you have two equations, two differential equations, two partial differential equations, one in x and one in h, and because of this, the space of solution will be finite dimensional. So now we can look a little more at specific cases. What it means that the telescoper is 1, so a constant. It means, in fact, that I equal directly to some power of dhy. So the power will be 0 here. And h, the big H here, it will be a rational expression. So it means, in fact, that I of xh will be some rational expression in x and y. So this is the situation when, in fact, the integral is exact. So you can express the integral of this rational expression in x and y as a rational expression in x and y. Now, if the operator is dh, then in fact this system becomes a first-order partial differential equation, and then you can rewrite a little and find that this function g here in x and y, which represents in fact this I of x and h, this will be the integral of closed one form. So it means, in fact, that when the telescoper is dh, the integral I is elementary. So in fact, this is the composition of an elementary function by x and y of xh. So in other cases where L is of higher degree, for example, then if we come back to this theorem, we see that we need to have either a Liouvillean first integral or a Darboux-Yan first integral, because the last two cases they are possible with Riccati first integral or no first integral, but the more complicated one require a first integral. So in other case, we need what we call an integrating factor. So in fact, the integrating factor here, it is just the y derivative of the first integral. Okay. So if you have first integral f of xh, of xy, then you can parameterize the possible solution of your planar differential equation, planar differential system, by the level of this first integral, because when you take a level, it gives you a solution. So we can assume that the parametrization for the solution we have chosen are exactly the levels of this first integral. And now this function g, this will be a solution of this holonomic system. So you have still the derivative in x of g, which will be the big J. So because this is the integration problem. So here I note big dx. This is in fact the operator, the differential operator acting on rational function in x and y. Because you can see y as a function of x, but you can also see it as an independent variable. So if you see it as a function of x, then you just differentiate in x. But if you see it as an independent variable, then the derivative in x, this corresponds to a Lie derivative of a two-variable function. And this, because of make this distinction, I used big dx. We can do the same for this big dh. This, in fact, this corresponds to the derivation in h. And with this new with the variable x and y, in fact, it is equal to u minus 1 times dy. And now our telescoper, in fact, is the second equation. So this is some operator dh, so big dh to some powers, so polynomial in big dh, apply to this unknown function g equal h. Now we can solve, in fact, this partial differential system because it is finite dimensional. And in fact, it has constant coefficients, so it's quite simple. So the solution of the homogeneous part are just exponential function times some powers. And then when you want to solve it explicitly, you find that this function g can be written like that. So a linear combination of some exponential of f, powers of f, and inside the integrals you have also exponentials, some power of f, some power of this integrating factor u, and these omega here they are rational differential one forms. So it means that somehow in this situation you can write the integral I not as an elementary expression, but still this is in fact some Liouvillean expression. So if you look closely, these are in fact integrals of differential form with exponential inside. And so this is not this is better, let's say, that in this general situation, and we will see in examples how it works. So first I want to show you that this existence of a telescoper is a generalization of elementary integration. In fact, if the integral is elementary, the integral of g of x and y of x is elementary, then in fact this parameterized integral I of xh admits a telescoper. So how we can prove this? So if this integral is elementary, then we can use this Liouville theory, which says that if it is elementary, we just need to add some logs. And because of this, this integral x of h, we should be able to write it like this. So a linear combination of logs of expression in x and y of xh, and some rational expression in x and y of xh. And what there is in front of these logs, there are functions, but we remember that when we differentiate this in x, all these logs should disappear because we should get back this rational expression g. So because of this, this constant, this function, in fact, these residues, lambda I, there should be function of h only. And now we can apply some operator, so which is polynomial in dh and holomorphic in h, such that now all these log disappears, and thus this operator L tilde applied to I will be some expression. So I write it polynomial, but in fact it is rational. Rational in x and y and its h derivative. And now I use the previous result, which says that if you have such kind of relation, then automatically the integral admits a telescoper, and more precisely a telescoper of the form we have seen. So let's present now an example to make it more concrete. You have this integral. So you see you have a power of x and these logs. And these logs, they also appear in the denominator, of course. So now this is not exactly what I've presented, but we can transform it by noting y equal log of x. So if I note log y equal log of x, I see that y prime equal 1 of x. So this is indeed a solution of a planar differential equation. And now my integration problem is that the derivative in x of I should be this rational expression. So of course, there is a first integral, which is exactly what we have written before. So y equal log of x. So the first integral, it is y minus log of x. And now this initial integration problem can be rewritten as an integral of an expression in x and y of xh. And we look at what happens when we move this parameter h. And it happens that we find a telescoper, this telescoper of order 4, and with the following certificate, so quite large already. So and when we try to integrate this partial differential system we obtain thanks to this telescoper, we find an expression for this integral. So if you look closely, so you have this log of 1 plus y. So y is in fact log of x. So we have already some tower of log. So this is allowed for elementary integration, but we have also these exponential integrals. So exponential integrals, so this is integral of exponential of minus x over x, I think. Maybe there is some convention on the signs. But anyway, it is not elementary. So if I replace y by log of x, I obtain an expression for my integral, which is not elementary. So, but still it is quite special, because if you look at what is in front of this exponential integral, you see you have x to the power 3 times exponential minus 3y. But if you replace y by log of x, you immediately see that this term, in fact, equals 1. It simplifies. But if you replace, instead of writing y equal log of x, you write y equal log of x plus h. So you change the level. Then what is in front of this exponential integral will be some exponential of, I think, minus 3h. You have also exponential minus 2h and exponential minus h. And of course, these terms, there will be inside the kernel of this telescoper. In fact, what is the solution of this telescoper? The kernel of this telescoper, they correspond to the functions which are the residues of this integral. So this parameterized integral. So now if I look at this as a two-variable function, I see that this expression, it is defined up to adding constants, because these exponential integrals, they are in fact integrals. So there are four new transcendental objects: the log of 1 plus y, the exponential integral of minus y, exponential integral of minus 2y, exponential integral of minus 3y. And because of this expression is defined up to adding some constants. So four constants. And this expression, they are in fact function of h only. So they are constant for the Lie derivative along the foliation. So there is another interpretation. Let's say if we look at this as integration of some complex Riemann surface. So if we think as y as a log of x, in fact, what we are doing, we are considering a function which is defined on the surface of the log. But because there is log also in the denominator, it means that there are infinitely many poles on this integral. There are infinitely many poles. And of course, these poles, they are poles of order 1. So it means that there are infinitely many residues. So this is not nice, typically. Because you have infinitely many loops to do. In fact, the integrand is defined on some infinite genus Riemann surface. But what is quite strange that, in fact, when you look at this monodromy, so you integrate along any loop on this Riemann surface and look at the values of the integral along this loop depending on h, you obtain a finite dimensional vector space of function. So here the dimension is 4. So this is what is quite strange. Maybe I should recall what happens in the elementary case. When your integral is elementary, it means that in fact these residues does not depend at all on the parameter h. They are constants. So here it's little more generalization because these residues can depend on this parameter h, but very specifically. So now I will present how you can find these telescopers. So first, I need to disclaim you that it's very hard to know that telescoper does not exist because they don't always exist. We are not in the algebraic case where they do always exist. And because of this, we just look up to some bound and we will see how we can do it quite efficiently. So first to remark, we'll study essentially a case where there is an integrating factor, because when there is no integrating factor, it means that in fact the telescoper is only 1 or dh. And in fact, in this situation, this is exactly the same as elementary integration. So, in fact, in this case, it's quite easier. But in a more complicated case, like in the K-Darboushian case, what we need to look. We need to look at some operator so with constant coefficients. Here the constant coefficients are the AI. When you apply this on I, it should be here this is a rational expression in x and y. And if you remember, there was this dh of y to the power L. But in fact, when you have an integrating factor, this dy of h, you can rewrite it as a function of u. In fact, this is equal to u to 1 over u. So after some modifications, you can rewrite the equation for a telescoper like this. Now we want to look for this telescoper, but as linear system. And this is difficult. Because you see, if you remove the denominator on the right, so you write p as a polynomial, then you obtain this q as polynomial on the left-hand side. But now you have, as unknown, you have what? You have the certificate parts, which are this p and this q, the numerator and denominator for the certificate. But you have also this unknown ai, which in fact are the coefficient for your telescoper. And because of this product, this unknown appears non-linearly. So there is a brutal method to solve this problem. Is to, instead of looking for this kind of telescoper, we introduce what we call a pseudo-telescoper. So instead of having just on the left the same polynomial q times the ai, we'll just generalize this to a random polynomial qi. And now, if you right-click like this, you see that if you look for polynomial p and qi, all unknowns will appear linearly, and so you can solve it in reasonably fast. And the good news, in fact, is that if you find a pseudo-telescoper, you can find a true telescoper. So this is what I say in this proposition. If you have a pseudo-telescoper, then you have an algorithm to find a true telescoper. So how we do this? So we start with this pseudo-telescoper. So this is a differential algebraic relation on I, and you differentiate in x. So if you differentiate this in x, so the derivative in x and the derivative in h commute. The derivative of x of I, this will be a rational expression, g, in fact, of x and y. So everything simplifies somehow, and you obtain a new relation. So this is exactly what we do in this reduced telescoper algorithm. We start from this initial pseudo-telescoper, where I write it L1. Then I differentiate in x. this produces a new telescoper. And then I try to reduce the order in H. So I write a big matrix. I look for linear combinations. I build this row echelon form, and then I find the minimal order relation. I can build like this. So now I can divide by the dominant coefficient and obtain this kind of pseudo telescoper a priori. But now there is a good news. In fact, we can prove that this pseudo telescoper, in fact, is always a true telescoper. These quotients, qi tilde over q r tilde, they are always constants, in fact. Okay. Now another question is how to check the result. If I give you a telescoper, how to check it is correct. By definition, if it is correct, it means that when you apply it to I, it gives you some rational expression in x and y multiplied by some power of u. So we can differentiate this in x. And what is nice is now the differentiation in x commutes with differentiation in h, sorry. And so everything simplifies, and you obtain some relation, so partial differential relation, only on rational expression. So you see g, this u, this h, and so you can check if it is true. Conversely, you can say, okay, if this derivation, if this relation is correct, can we go back? So in fact, almost. We can integrate in x, but when you integrate in x, you remember that you have this parameter h, so you obtain the same relation as before, but plus this function f of h. So it seems not so nice, but in fact, the good news is that this integral I of xh, h is a parameter. So because of this, the integrate I is defined as some integration in x. So in fact, it is defined up to addition of some random function in h, because h is a parameter. So we can correct this expression by adding to I some function of h, satisfying this differential equation. And if you do this, this will exactly correct this f of h and simplify, and then you go back exactly to the initial equation for the telescoper. Okay, so how we can find telescoper in this approach? So first we need to introduce some bound m. So I need to precise what is these letters. So big N, it will be the bound on the degree of the certificate, because we need that the user give bounds, because else I am not able to have a general algorithm to find telescoper, because they don't always exist. So the user needs to give bounds. So we put n for the degree of the degree of the certificate, and odd, it is the degree of the telescoper. So this k disappears when this k Darboxian. So in fact, when it is Liouvillean, you put k equal infinity and it works. So introduce this big M, which is constant, integer typically. Now I compute series in series these h derivatives of our integrand g of x and y of xh. So you just take initial condition and you solve in series your differential equation. Then so of course with dependence on the initial condition, and then you obtain series for this LG. Then you compute these integrals, so you have powers of y and these integrals, and then you look for a pseudo telescoper which will vanish on this expression at I order, in fact at order m. So you can do this fastly with Padé-Hermite approximation, and if you find a non-trivial solution, then this will define a pseudo telescoper T. Then you apply this algorithm reduced telescoper. This will give you, in fact, a true telescoper. Then you check it, and if it is correct, then you have found a telescoper. And if it is incorrect, it can be. Then it means that somehow you have chosen a bad initial condition. So when you make this series expansion, you need to find to choose an initial condition, and there are bad ones. Maybe I should go faster. What is the result for this algorithm? So if the integral admits a telescoper satisfying the bounds, then it will find it. If the algorithm returns none, it means that there is no telescoper satisfying the bounds. And if the algorithm returns fail, so it means that you have chosen a bad initial condition for your series expansion. It means that this bad initial condition belongs to some exceptional codimension 1 algebraic set. And the complexity is quite okay. So you see it is typically power 4 in n. Okay, so let's look at more interesting, let's say, examples. So again, let's say with this foliation log of x, if I consider this integral of x squared over log of x squared, I find a telescoper of order 1. And then when I integrate it, I find an expression, again, using this exponential integral. So there's another one a little more complicated. And here you see you obtain exponential integrals, logs, but also this polylogarithm. Logarithm integral of this polylogarithm. And this I3, this is maybe this is the same as before. This is a rational expression in x and log of x. Again, you find a telescoper. So this telescoper is just dh, and it means that in fact this integral is elementary. And indeed, we can find back this elementary expression for E3. You can also have mixed situations like this one, I4. So you have a telescoper of order 2, and the integral can be written as log of x plus log of x, you see, plus also this exponential integral. I have made some benchmark on these integrals, which can always be written with exponential integrals. And here you see the timings depending on the size. So in fact, it is related to the degree and number of poles here, this small n. So of course, the time grows very fast. But it's reasonably fast, reasonably possible for, let's say, compact expressions. Another one with exponential, again, it can be written as an integral on some foliation with x minus with x equal log of y. So again, you can write it as an integral of rational expression in x and y. Again, you find the telescoper, and this means that this integral can be written again with these polylogarithm functions. In fact, in this situation where you have just integral rational expression in x and log of x, I have a more complete understanding of what you can obtain. In fact, the integrals which admit the telescoper, so rational expression in x and log of x, they can always be written like this. So linear combination of this exponential integral, a linear combination of this logarithm of the polylogarithm and powers of logs, a linear combination of logs, in fact, and rational expression in x and log. Okay, so then there are more complicated examples. Here you can see this integral I6, where you have inside some hyper-exponential function. So you have the x with something with the x to the power square root of 2. And again, it admits a telescoper here, and you can find an expression using this Lerche function. So in general, the expression you obtain, it does not always, it is not always possible to write it with special functions, but it is always possible to write it with holonomic functions, because at some point you have a definite system, so you can always solve it with holonomic functions. So you have another examples with Airy functions. So if you take this integral with Airy function, so this quotient I prime over IE satisfy again the first order differential equation. So it is the case of Riccati first integral. So you obtain this time an integral which is elementary, and here you see the telescoper in fact is just dh. Maybe I will go faster. So this is an example with elliptic integral of the third kind. Okay, and maybe let's go directly to this last application. that I teased about. It is the application to integrate a planar vector field. So let's consider, for example, this differential equation on the plane. So x dot equals some rational expression in x and y dot equals some rational expression in x and y. And we want to find the Liouville expression for this solution. So the first, we try to express y in function of x. So you can make the quotient of these two, and you obtain a differential equation dimension 1, non-autonomous. And it appears that this differential equation admits a Darboux-Yan first integral. So I have a work with Guillaume Chaise, which look for this kind of first integral automatically up to some bound, and which can work quite efficiently on these sample examples. You can get back this integrating factor, which is just the y derivative of this expression, u. And now to perform the integration in time, you need to integrate this. So we need to integrate this expression on the level of the first integral. So the good news is that in this case, a telescoper is found, and we can manage to find then quite explicit expression for the solution. You see here the first line is in fact the first integral, and the second one is the integration of this here, and this is equal to time. So in fact, when you find a telescoper, you are able to solve this planar differential equation as an implicit system, but which is no more differential. You have transcendental functions, but here you see x and y are written implicitly as a function of t, the time here, and these two constants of integration, c and h. So, thank you.
Okay, Thierry, thank you so much for your interesting talk. Do we have any questions or comments? You can just unmute yourself and ask, or if you prefer, you can also type it in the chat.
Hi, it's Michael Singer. Can you hear me?
Yeah, yes.
Okay. Thanks. This was a very nice talk. I have two questions. One is the first result, the theorem you mentioned about if that there are four possibilities, or this thing becomes differentially transcendental.
Yes.
So is this an argument based on a holonomy group and a classification of that?
So this result from Guy Casal in his thesis about Malgrange pseudogroup.
Okay, okay. And the second question, if I can, is that in the usual approach to telescopers, in the algebraic case, the existence depends on, well, you look at a certain class of one forms and you show that they are finite dimensional and invariant under differentiation.
Yes.
So do you have this, a sense of differentials of the third kind in this context? And I assume they become infinite dimensional.
Yeah, yes. So if you think, for example, you take an integral of some algebraic expression, depending on the parameter, and let's say you have an integer parameter which encodes the algebraic degree of your integrand. So what happens is typically when this algebraic degree increases, the order of the telescoper increased. Because in fact, you are integrating on the Riemann surface with growing genus. And typically the order of the telescoper is 2 times the genus. So when you are in this situation, transcendental situation, the genus in fact is infinite. So in the generic situation, there will be no telescoper, or maybe I don't know if it is possible to write operators as infinite series or something like this, but at the limit, this is what we obtain. So here, this is all the examples I've presented are very exceptional by the fact that a telescoper of finite order exists. So, for example, if you take the integrand 1 over x plus log of x, so it was a quite known example of Malgrange. In this situation, there will be no telescoper. So, and this is the generic situation. So
So is it a question of somehow the representation of a homotopy group on this space and looking for finite dimensional invariant subspaces?
Yeah, yes, this is more or less like this. Yes, so when you look at if you look at this as complex functions, so the integrand is defined on some Riemann surface and depends on this parameter h, which in fact is more or less some translation. And you look at residues. So you have typically you have infinitely many poles, so infinitely many residues. Each residue, this is a function of this parameter. And then you look at the vector space of function of this. So typically you assume that it should be infinite dimensional, but in fact, in all the cases I've presented, it is finite dimensional. And in fact, what I've proven is that when it is finite dimensional, there are only exponential polynomials.
Finite dimensional as a complex vector space.
Yeah, yes, finite dimensional complex vector space.
But okay, thanks.
Okay, are there any other questions or comments?
Yeah, can I just ask, I'm sorry, the infinitely many residues. I'm sorry, for which function again? I'm sorry.
So if you maybe the simple example is let's go back to let's choose. So let's choose I1 for example. Okay. So where no I1 is there is a multiple pole. Let's say I2. So look at the poles. So you have x plus 1 and log of x. So when does it vanish? So when x equal -1 and when log of x equals 0. So you can think, okay, there are only 2 poles, but no, because this log of x, it is multi-valued. So this function is defined not on the complex domain, but on some ramification, infinite ramification over C. And so, for example, this point x equal -1, it generates infinitely many residues. For each level of the log, this gives you a point. And if you compute the residue at this point, it will depend on the level on this Riemann surface.
Thanks.
Okay, any other questions?
Well, I don't know if this is the right question, but in all these examples, you're given an integral to do, and then you somehow know what y should be. That has to satisfy y prime equals of fx of y of x.
Yes.
Now, the first question is, well, how do you find y? Well, is it the generators for the base field fx comma y
somehow
so you can integrate?
This is what we require from the user. So the user should give us a rational expression in x and y where y satisfies some first order differential equation.
No, but you're given some integral to do, and then you have to find the y, right? So
no, normally it should be the reverse. So of course, for classical stuff like log, you want to introduce y equal log of x. But a priori, I should not. It should not be done this way. It should be written as a expression in x and y, and the y should be defined as a function. Here you see y is defined, in fact, as a solution of the differential equation dxy equal 1 over x. Normally, if I do this purely algebraically, this function log should never appear. I should write only y. And I consider this integral as of x of the integral x and y restricted to some curve, which is y minus log of x equal h.
Okay. So I mean, in terms of a differential field, like cx and then y of x, which satisfy your condition, what kind of integrals
So it means that they are transcendence degree 1.
What would be one?
Why? If you look at the differential field x and y, when you differentiate y in x, it is again a rational expression in x and y. So this is a differential field, and its transcendence degree is 1.
Right. So the question is, what elements from this base field can you find the integral?
This is very difficult.
And how big a field, extension would you need? So you may need the EI and all the exponential.
So very small, very small parts. So if you look back at this proposition here, you see that the integrals admitting a telescoper. So for this case with the log, so it's more than elementary ones, because so the elementary part is the second line, but not so much more. You have these logarithm integrals and these exponential integral. So when I say not so much more, it's infinite dimensional. So if you look at the integrals quotiented by the integrals which can be elementary integrated, it is still an infinitely dimensional vector space.
Okay.
So it's not so small, but still it's countable. So I don't know, in fact, but I have the impression that it is a very rare situation still.
Is there some concept of a kind of integral closure that can use telescopers?
It's not closed. So yeah, I don't know. Because so to have a closure property, we need understanding on the integral, on this kind of integral, but in the general situation. And I don't know. So as I said before, in the algebraic situation, what is good is that in fact we are integrating some function defined on some Riemann surface of genus G. And because of this, there are not too many loops, and you can kill them with some operator of finite order. Here, typically, the genus is infinite. So the operator we should need would be infinite order. And I'm not sure about convergence properties and so on. Maybe there is some analytic stuff which can be done, but
okay, thank you.
Okay, any other questions? All right, this does not seem to be the case. So let's thank Thierry again for the nice talk. And so I'm looking forward to seeing you all next week.